Hi, for this video, we're going to look at efficiency in thermodynamics. Some examples for that. The first example is from WebWorks. It said a pump is used to increase up the pressure of fluid, and this is done by converting the shaft work into the mechanical energy increase of the fluid. They told us the increase of the mechanical energy is 4.95 kilowatt here. They also tell us the pump is expanding 7.2 kilowatts at the shaft. So knowing the efficiency eta for the pump is desirable output, which is in mechanical energy increase of fluid over required shaft work. So 4.95 divided by 7.2, we get our efficiency. Very simple example, and that's what we call low-hanging fruit for this problem. Now let's look at this example here. And for this one, they told us this is from textbook. It's hydroelectric power. Hydroelectric power, this is something we just need to know, is hydro means water, so you use water flow from high altitude since it has like high potential energy. They convert that mechanical energy of the fluid to this shaft rotating here, and this shaft rotating inside the magnetic coil, so that generates electricity. Okay, so they told us there's a volume flow rate V dot is 65 meter cube per second of water flow at elevation of 90 meter. Then electric power is generated. The overall efficiency of this turbine generator is 84%. So this overall is 84%. Disregard any frictional loss. They want us to find out electric power output of this plant. Okay, so overall of the turbine generator is your desirable output, which is our electrical work, right? So it's energy of the electrical work output. And the very original required input for this is going to be decrease of the mechanical energy of the fluid. For this case, it's water. Okay, so then we needed to figure it out how much that is. They want us to figure out electrical output, so this is basically what we need to figure out. And so the question is, can we find decrease of mechanical energy of water? Can we? All right, let's think about. Then mechanical energy decrease of water, that's going to be mg delta h, mgh. Now let's think. And since this is in watt, this is in energy, so this is in joule. But if you want to get watt, we have to divide by time. So if we were trying to divide this by time, what would we get? We have mass over time, so that's going to be mass flow rate, GH. That's going to give us a unit of watt. Okay, do we know the mass flow rate? Or how do we find mass flow rate? We know the volume flow rate. Volume flow rate times density give us mass flow rate, right? So volume flow rate here is 65 meter cube per second. That's a given volume flow rate. Density of water, we know it's 1,000 kilogram per meter cube. Knowing those two, we know we're going to find our mass flow rate, which is 65,000 kilogram per second. Knowing mass flow rate, we can plug back into this equation. We can find our decrease of mechanical energy of water is 65,000 kilogram per second mass flow rate times our G, which is 9.8, and our height decrease is 90 meter. then that would give us a unit of watt, since we're using kilogram per second mass flow rate. So if I were trying to put it in there, 65,000 times 9.8 times 90 will have a big number. Then if we were trying to change that in kilowatt, so kW divided by 1000, I have 57,330. Okay. And if we were changing that to megawatt, we're going to divide it by 1000 again. So that would be just 57.33 megawatt. That's how much energy was input into this turbine to turn this shaft. And then the shaft is trying to generate electricity. They give us the efficiency is 84. So now we calculate this one is 57.33 megawatt. Then would be really quite simple for us to figure out this electric output, right? So this electric work will be just this 57.33 megawatt times 84%. Then put in the calculator, we got 48.2 megawatt. Okay. So that's for this problem. All right, I'll see you next one. Bye.